Hey guys, thanks for coming back. Good to see you, or something like that. But believe it or not, this may be one of the last videos of this semester. Maybe I'll come up with another one, who knows. But anyway, it's kind of sad, isn't it? Not really. We're all anxious to get this over with. But calories, measure of heat energy. Calorimetry, the science of measuring heat. The flow of thermal energy. Do you ever notice how some things warm up and cool off faster than others? Some things are good thermal insulators, and some things are conduct heat really well. Like usually metals conduct heat really well, and ceramics. But things that don't conduct heat very well, water and ice even, believe it or not, it's a good insulator. But these are called specific heats or specific heat capacities. And the larger the number, the slower the substance responds to heating and cooling. And we'll use that. I think we've seen this equation before, but if not, we'll use that in my heat equation. It goes Q equals M times C times delta T, something like that. There actually are various different conventions, agreements, so maybe there's not an agreement on how this should look, but important in terms of calculating how much heat flows is the mass of sample. How much of the item of the substance are we talking about? The degree in change in temperature, like is it change 1 degree or 10 degrees or 100 degrees, and how that specific thing, that certain substance responds to heating and cooling. Sometimes scientists use one calorimeter device over and over again, and they might combine the M and the C to get something like that they can use over and over again. And so what I'm saying is sometimes they will multiply these two together and just use that term over and over again and just measure how much the temperature changes. Well, I guess that makes sense to save them time. The heat capacity is how a substance responds to heating and cooling. And actually the larger the number, so the smaller the increase in temperature per heat absorbed, the larger the heat capacity. So water is like the champion of specific heat. It responds to heating and cooling much slower than anything else. Sometimes you'll see this CS, our textbook uses a little s, which I suppose is okay, but I'd rather use capital C as more common. Joules per gram degree Celsius, or if they put it in moles, it's joule per mole Kelvin. And if I know what that substance is, the chemical formula, it would be pretty easy to change grams to moles, but actually, I think this one's more common if I dare stick my neck out. But we'll end up remembering this one, 4.18 joules per degree Celsius, per gram degree Celsius. So if I had a gram of water and I wanted to raise the temperature 1 degree Celsius, all I have to do is add 4.18 joules. And I can do that easily. I always squirt a little bit of water in my hand, call that a gram, and my hand warms the water up by 1 degree Celsius, and I imagine that to be 4 joules of energy. So a joule is not really that much energy. That's why many times we'll see the numbers coming out in kilojoules. And which reminds me, this might be a typo. What is 43.7 times 0.385 times 30? I think it's more like in the order of 505 kilojoules. Let me calculate that, see if I made a mistake. No, that's right. And I suppose I'm used to doing this heat equation for water. And water has a specific heat of 4.18. So that's like 4 to 10 times, 100 times larger than... That's 100 times larger than this, right? No, is it? But 10 times larger than this. Anyways, so the answer is 505 joules. And in that sense, I'm saying, would it take much heat energy to warm copper up 30 degrees Celsius? And the answer is no, because copper responds quickly and easily to heating and cooling. Interesting, yeah? Here's another example. Two substances are mixed and the temperature is monitored. And the substances are an acid and a base. I forgot to write aqueous in back of this NaOH, but it's aqueous. It's in the water, just like this HCl. So in the water, I have 50 milliliters of 2 molar in one beaker, styrofoam cup, and 50 milliliters of 3 molar NaOH in another styrofoam cup. And the reason why I choose styrofoam, you know why? Yeah, you do. It's a good insulator. Usually we do chemistry in beakers, but in styrofoam cups, they help keep the heat in or out help insulate things really well. Temperature rises, so an acid plus a base, exothermic reaction from 21 to 34 and 34.9. And here's my net ionic equation. 1 mole of acid, 1 mole of base. And the specific heat capacity for water, and most fairly dilute, even though these are sort of concentrated, we'll assume it's still close to 4.18 joules per gram degree Celsius. And let's figure out the delta H for the reaction. Delta H and Q are very closely related, although delta H is usually given per mole. Oh yeah, so by the way, this is a mean question. It's only mean because it's a limiting reactant question. If I had 2 molar 50 milliliter and 3 molar 50 milliliter of base acid, I did a little math and see I have extra NaOH and limiting H plus or acid. So 100 millimoles of this reacts with 100 millimoles of this to create 100 millimoles of this, leaving 50 millimoles of this remaining in the beaker unreacted. But in any case, my heat equation would say that 50 milliliters plus 50 milliliters is 100 milliliters, and a milliliter of water is also a gram of water. So that's why I wrote 100 grams of water here, times 4.18 times the change in temperature, ending minus beginning. Comes out to 5,810-ish joules, and that's also 5.81 kilojoules. But you know what? Like I was saying earlier, the delta H and the Q, delta H is Q per mole, so I took that and per mole, and I had 100 millimoles, which is also called 0.1 moles of this reacting. So I did divide by the moles of stuff reacting. Comes out to 58 kilojoules. Also, this seems weird, but physicists and chemists do this sometimes. We'll just throw a negative in there, throw a negative in front, because I know it's exothermic, and I know delta H for exothermic reactions is negative. So that seems bogus or hokey pokey, but hocus pocus, what I'm trying to say. But I just throw a negative in there to make it agree with everybody else. And to make this agree with this, we throw a negative in front there. All right. So, trust me or not, that's the way it goes. Sorry. Silver chloride, silver ion plus chloride ion. 100 milliliters, 0.15 molar, 100 milliliters, 0.15 molar. Many times it'll be a 1-to-1 ratio. And I'll have the equal molar amount, equal molar and equal moles of this, equal moles of this. So it looks like, what's 100 times 0.15? What, 15 millimoles of chloride and 15 millimoles of silver ion to make 15 millimoles of silver chloride. And the temperature increases 1.2 degrees, not very exothermic, but still. And if we go 100 milliliters of this and 100 milliliters of this, that's 200 milliliters. And if 1 gram is 1 milliliter, then I'll have 200 grams of solution as well. It'll be, whoa, that's kind of a, increases 200 grams of water by 1.2 degrees Celsius. That's quite exothermic. I didn't really think it was that exothermic. I swear I didn't make this question up, but all right, whatever. So 100 milliliters of the silver ion and chloride ion and yada yada, and the 200 grams, which is 100 milliliters of silver ion water and chloride ion water, temperature increase. That's about 1 kilojoule. 1003. Let's see, how many sig figs am I talking about? Probably just 3 sig figs, right? Yeah, I'll have to round that off later to 3 sig figs. But if I'm going for kilojoules per mole, anyways, then I'll save it until the very end. And the moles, I had 15 millimoles. Yeah, 15 millimoles reacting. And 15 millimoles is 0.015 moles. And so the heat, the Q divided by the moles, and I should stick a negative in front too, right? So negative 66.9 kilojoules. And this is, I'm serious about this. I did dissolve potassium iodide in water for a fun demonstration. Made a mess afterwards, but anyways. 40 grams of Ki and 50 milliliters of pure water. And I estimated the specific heat to be, now honestly I made this up, but it's a good estimate, 3.95 joules per gram degree Celsius. The temperature fell from 22 to 10.7. What's the delta H for this dissolution? Delta H is solution, dissolving that Ki into water. Well, if I had 40 grams here and 50 grams here, I'm estimating 90 grams is the mass, total mass of the solution, and the specific heat capacity, and the change in temperature. And lo and behold, I get a number. This Q came out negative, So if this Q came out negative, I suppose that means it's endothermic, because I suppose it also means I'm going to have to change my ending delta H not to be negative, to be positive, because endothermic processes have delta H's that are positive. So I changed grams to moles for the Ki just because I know I'm going to need to divide the Q 4.02-ish kilojoules by the moles. And to find the delta H by convention, I'll change that negative to a positive and divide kilojoules by moles, and voila, there you go. Interesting. Oh, one last example. I took this right from my lecture notes. I put a hot copper penny into some cool water, and I was trying to estimate the temperature of the flame it came from, the mass of the coin, the specific heat of the coin, the change in temperature of the coin. So I got a warm coin. I'm going to drop it in some cold water. This is kind of a hairy calculation, but a good one to look at once or twice. I don't know if I would expect one like this in the final. It's kind of involved. Who knows? It's good to look at, good to think about. The mass of the water, specific heat of the water, change temperature of the water. The heat kilojoules lost by the penny is equal to the heat kilojoules gained by the water, except they're opposite in sign. So you got to stick it to a negative in front of one of them. One of them's gaining, one of them's losing. Doesn't matter which one you stick the negative in front, actually it comes out good either way. So the mass of the coin is copper, so the specific heat is 0.385-ish. Change in temperature, this TF minus TI, those will be a little bit different than this TF and TI. Like the TF of this will be the same as the TF of this, right? Yeah, right, it will be, because the coin and the water come to the same final temperature. But the TI of the coin is very, very hot, and the TI of the water is room temperature. So I did this multiplication, so this multiplication simplifies, this multiplication simplifies. So this one and this one are the same, but the fire is definitely hotter than the initial temperature of the water. Let's do a little bit more algebra, and temperature of water, temperature warmed up by 5 degrees. Let's call it 5.0 degrees to make at least 2 sig figs. I like to keep 3, but whatever. So this multiplies out. The only thing I don't know now is the temperature of the fire. Solve with my massive algebra skills for that, and it comes out to 900 Celsius. 2 sig figs, 3 sig figs, somewhere in there. Yeah, so that's it. That's the heat equation. Thanks for watching, guys. I'll see you in class. Good luck in your studies. Don't give up. Don't let up.